Alright, let's talk about projectile motion a little bit more. This is the same graph that we used before, literally, showing the x and y position of a projectile if it was launched with some vector or some initial velocity v0 at some angle of theta. So that's right there. In this case, we see that the y component goes to 0 and the x component remains the same. The velocity in the x direction is the same in every spot, unless we have drag or something, but I'll talk about that shortly. Let's go ahead and note that the x position could be denoted always as the magnitude of the velocity times the cosine of that angle theta times time. So this is our v0 then. So that's just x is equal to v0 times t, right? Okay, and then we had one more for the y coordinate. Y final minus y initial is equal to the y component of the velocity, v sine theta, times time. And then we have one more term. In this case we have the acceleration term. This one we didn't, right? There was no 1/2 at squared. This one had the 1/2 at squared, but it was actually gravity. 1/2 the acceleration due to gravity times time squared. And in this case we need to put in negative 9.81 meters per second squared for gravity. Okay, with these two equations, 1 and 2, we showed that we can make the equation of a path in the last video. So it literally didn't have time anywhere. It only had coordinates, angles, and the initial velocity. Well, from these equations we can also get what's called the range. And the range is literally just how far it goes in the x direction. So this would be our range. And when we calculate range, it only works when it lands at the same altitude it took off from. So when y final is equal to y initial. That doesn't mean we can't calculate some point up here and call it y final. But I mean the actual point it hits when it's done traveling, that's our y final, is at the same altitude as what we launched it from. So same altitude. We can't basically launch something off of a building and use the range equation to figure out how far it goes. We have to derive a slightly different equation. So what we can do is set x minus x0 equal to what we're going to call the range. And since there is no change right here, our delta y is actually equal to 0. And we end up getting the range equal to v0 cosine theta times time. And then 0 is equal to v0, the y component of the velocity, times time. And then we have the 1/2 gt squared. Alright, what we can do is eliminate eliminate time. So however you want to do that, this one I think I would solve for this t and substitute it back in. Doing so will give you what's called the range equation, and we get the range is equal to 2 times the initial velocity. That's not in any direction, this is just v0, so that would be the magnitude of whatever you launched it at, all over the acceleration due to gravity, times the sine of the angle, times the cosine of the angle. And we're going to get rid of this, but check this out. We're calculating how far something goes, only knowing our angle and the velocity we shoot it at. Well, that's convenient, right? If we know the magnitude and the angle it's shot at, and it comes back to the same point you shot it from in the y direction, then we can just use the range equation. The substitution we're going to make here, though, is that the sine of 2 theta is equal to the sine theta cosine theta. You probably remember that from back in the day, maybe pre-cal, I would say. Oh, there's a 2 right here. There we go. So if I move the 2 to the other side, I'd get the sine of 2 theta over 2 is equal to the sine theta cosine theta. And let's replace this whole thing right there, leaving me with the range equals to 2 v naught squared over the acceleration due to gravity times the sine of 2 theta. So once again, all we need is v naught and theta, and we can figure out the range. Ding, ding, ding. Good to note, if we don't have any drag or air resistance, so if we shot this in a vacuum and we were looking at the y and x-axis like so, and let's say we shot it with some initial velocity looked like this. If that velocity is shot at an angle of 45 degrees, we will get maximum distance. Oh, hold on. Try that again. So that will give us, damn, that was good. Sorry to brag, but that was a pretty damn good parabola. That'll give us our maximum distance. Alright, now let's see what would happen if I shot it at maybe positive 60. It's going to go higher, and it's going to come back down and not make it as far. If I shot it at maybe 30 degrees, it is not going to be in the air as long, so it'll actually end up going the same distance as 60.